Hi everyone, my name is Brandon Laguerre and this is the final presentation for Group D. Our project is the Distributed Sound Event Location System, also known as DIESEL. On the hardware team, we have myself and Chris Santana, and on the software team, we have Mark Judy and Drew King. For both humans and animals alike, the sounds we hear play a major part in allowing us to communicate and quickly make observations about the world around us. However, we're not always here to hear these sounds, so the main goal of this project was to use technology to convert the surrounding sounds into more useful information. This information can be used for many things, such as increasing safety and security, research, conservation of animals, or general hobby activities. We wanted to achieve this using a few major steps. First, a sound event will occur that will trigger a network of audio sensors. The GPS and sound data from the sound event will then be sent to the sensor server to determine the location of the sound and store the audio information. Then, this sound will be classified and sent to the web server, which will display the ID and location of the sound to the user. For our engineering requirements, we knew that we wanted the sensor server to analyze sound events from multiple sensors. We also knew that we wanted the sensors to timestamp all the audio that is transmitted to the central server. The sensor server will determine the location of the sound event using time of arrival. A separate machine learning server will access the audio data from the sensor server and perform classification predictions. Finally, a web application will give the user access to all information obtained and processed by the system. For our engineering specifications, we wanted to identify the originating location of the sound event within 10 meters, classify bird calls with greater than 70% accuracy, have a maximum operating distance between sensors greater than 50 meters, classify a bird call within 10 seconds, identify sound event location within 10 seconds. The middle section of this figure shows our overall block diagram. As you can see, our block diagram shows we have our sensors, which will then lead into the wireless protocol, the central server, and in the web interface. At the top of the screen expands upon the sensor block diagram, where we have the power supply that feeds into the microcontroller and the rest of the PCB, the microphone, which will receive audio data, the GPS module, which will receive satellite and GPS data and send that to the microcontroller. And then the microcontroller will send that information to the wireless module. The wireless module will then send the GPS and audio data to the central server, where the central server will do sound detection processing, sound classification algorithm, time of arrival analysis, our multilateration algorithm, and then finally it will send that to the website hosting software, where the user can see it on the web interface. Up next is the hardware design portion of this presentation. On this slide, you can see our overall PCB schematics. On the left-hand side, you can see our Wi-Fi module schematic, which is attached to our microcontroller and bootloader schematic on the right-hand side. Continuing from the last slide, you can see our DC to DC converter circuit on the left-hand side for the battery module portion of the PCB, and on the right side, you can see the auto shield that we use to record the incoming audio data. On this slide, you can see our printed circuit board design. Our PCB is 2.59 inches in width and 3.8 inches in length. PCB manufacturers typically charge based on square inch, so it was really important for us to keep the PCB as small as possible. On this slide, you can see the finalized manufactured PCBs. On the top right is the bare board, and on the bottom right is the board with all the components soldered onto it. Our PCB manufacturer was Oshpark for two main reasons. One, they have a tool that makes it really easy to upload from Eagle, and also lets you set the settings on Eagle. And two, it has a really quick turnaround time, which is really good for testing. 3 PCBs were manufactured from Oshpark for this project to make up the network of sensors. On this slide, you can see all the parts that make up the PCB. At the top, we have the antenna for the GPS module, then we have the bootloader, then the microcontroller, the audio module, the Wi-Fi module, and then the GPS module. Our first step in the design process was to pick a development board to use to prototype the project. Initially, we wanted to use an MSP430 due to prior experience in other classes. However, we later decided that we wanted a more powerful processor to use. So that left us with the Raspberry Pi, the BeagleBone, and the Teensy 3.2. The BeagleBone is pretty quickly ruled out due to it being a little overkill on the processor speed and also the high price tag of it. That left us with trying to decide between the Raspberry Pi and the Teensy 3.2. The development board that we ended up using was the Teensy 3.2. This is primarily due to the fact that the Teensy 3.2 can be programmed using Arduino and also allows the use of the Teensy Arduino audio libraries, which are really powerful for a project like this. The Teensy 3.2 houses an ARM Cortex-M4 processor that has an operating voltage of 3.3 volts, a maximum clock frequency of 96 MHz, 34 I/O pins, a RAM size of 132 kilobytes, and has I2C, I2S, SPI, UART, USB OTG, and CAN as communication protocols, most of which are going to be very useful for this project.
For the batteries, we compared lithium ion, nickel metal hydride, and lithium iron phosphate batteries. After comparison, we chose the 18650 lithium ion battery. It has a typical voltage of 3.7, but actually can be charged to 4.2 volts. We chose this battery because of its popularity, as it is found in flashlights, laptops, and power tools, and also has a low self-discharge rate. For the charging IC to charge the battery, we compared the TP4056, the MCP73831, and the MAX8900A. After comparison, we decided to go with the TP4056 because it is well documented, widely used, and is decently priced. Our power supply uses a battery management system, or a BMS. The purpose of a BMS is to prevent overcharge, prevent over-discharge, and ensure that each battery is charged at the same rate. For our project, we used two TP4056 charging circuits. The TP4056 is a lithium-ion charging IC, and it charges with constant current and constant voltage. And it charges these batteries to a maximum of 4.2 volts. To add protection for the batteries, a DW01A IC is used in the charging circuit. The DW01A offers two main features: overcharge protection and over-discharge protection. If the battery voltage goes above 4.3 volts, the DW01A cuts off power to the battery. Once the battery voltage drops below 4.1 volts, the DW01A will restore power to the battery. If the battery voltage drops below 2.5 volts, the DW01A cuts off battery voltage from the output. The DW01A reconnects the battery to the output once the battery voltage goes above 3 volts. Since the two TP4056 charging circuits are connected in series, they share a ground at the input, and this means that they cannot share the same power supply, or else one charging circuit will be shorted. To fix this issue, a B0505S was used, which is a DC to DC converter with isolation. The B0505S takes an input of 5 volts and outputs 5 volts, while at the same time isolating the input from the output. This allows both charging circuits to be powered using a single input. For the solar panels, we compared monocrystalline, polycrystalline, and thin film solar panels. After comparison, we decided to go with the monocrystalline solar panel because it is the most efficient, meaning it'll save on space and will work better in bad weather and low light conditions. This is our monocrystalline solar panel. It is 40 watts and outputs an unregulated voltage of 18 volts, but also outputs a regulated 5 volt output at 2 amps. And this is done through a USB connection. The audio module is what records the sound events. So we focused on high sound quality. We compared the Sunfounder USB mini microphone, the TI audio signal processing booster pack, and the Teensy Audio Shield. We decided to go with the Teensy Audio Shield because it interfaces well with our Teensy 3.2. For the Wi-Fi modules, we compared the ESP32 Room, the Simple Link Wi-Fi CC3120 booster pack, and the ESP8266. We decided to go with the ESP32 Room because it can communicate through SPI and is well documented. For our GPS module, we compared the Neo 6M, the Neo M9N, the Adafruit Ultimate GPS, the Adafruit Mini GPS. We decided to go with the Neo 6M because it was the cheapest and had UART communication.
Hi, my name is Drew King. We will now discuss the software for our project. The classification problem for our project was to classify a bird species by their bird call alone. To solve this problem, a CNN was trained on bird call data of 29 different bird species. To make the use of the CNN, the data needed to be converted into an image representation of the audio signal. To do this, feature extraction, MFCCs, a popular way that is used for speech classification, was used utilizing Librosa. The classification results were then sent to the web server to be stored within a MongoDB database to be accessed by the user interface. To train an accurate model, a large set of data is a necessity. One issue that the classification of bird species through audio is the lack of actual data. With use of Xenocanto, a crowdsourced bird call web interface and API, a dataset consisting of 29 different species, each containing 100 samples with a minimum duration of 30 seconds and a quality based on the scale provided by Xenocanto ratings between an A and a B. All the used audio data came with a Creative Commons license that allowed for its usage. To train the CNN, some normalization must occur with the data. The duration of the data must all be the same. For this, each of the data samples were cut to a standardized length of 30 seconds, which was the minimum duration of the samples obtained from Xenocanto. To increase the number of training samples, each 30-second clip was divided into 6 even segments of 5 seconds apiece. This displays the MFCC of a .wav file containing audio from the used dataset. The MFCC represents the coefficients that collectively create a mel frequency spectral. These extracted features are then being used to train the model. Python was used to write the script used to train the classification models. This is due to the fact that Python is one of the most popular languages to complete these types of tasks, and there are many resources to help in this process. Since the training of CNNs is computationally heavy, a GPU was used to help increase the speed of the model. This allowed for more model architecture to be trialed. Since the nature of building an accurate model requires some trial and error and continuously architecture tweaking to obtain the most accurate model, the popular framework Keras was used to implement the training, validating, and testing of the model, along with using TensorFlow as the backend. The CNN consisted of multiple layers. This included 7 convolutional layers, starting out with a single layer of 32 nodes, 2 64-node layers, 3 128-node layers, and finishing with a 256-node layer. A dropout of 10% was implemented after alternating convolutional layers to combat overfitting. A flattened layer was then used to convert the data into a readable format for the final dense layers. 2 dense layers were then implemented, one with a size of 128 nodes and the second consisting of 64 nodes. Both had a dropout layer placed after each of them, and a final fully connected output layer was used for the 29 species. We used the atom optimization function along with a sparse categorical cross-entropy loss function. The CNN model and its neuron weights determined during training and testing were saved within a .h5 file. This file is then loaded onto a dedicated server specifically created to run the classification model. To implement this model on the server, a Flask server container was created. This was extremely useful since the Flask server is written in Python along with the model, allowing the use of the valuable audio libraries provided in Python. New data from the sensors can then be classified live without the need of retraining the CNN every time a classification is needed. The model during training and cross-validation achieved an overall accuracy of 73%, classifying 29 species of birds based on the sound of their call. The real-world testing with our system outperforms the overall accuracy, however this is achieved on a much smaller sample size. For our web application, we use the mean stack. This is due to the use of JavaScript throughout the stack and the benefits provided by that continuity. As shown in the figure, the application will use AngularJS for the front end, Node.js with Express for our server, and API, and MongoDB for our database. The login and sign-up component of the web application are the first thing that a user interacts with. The login process is quite standard, with the user entering their username and password. Those entries are then sent to the web server that first queries the database to see if any of the database entries contains a username that matches. If this query returns true, the web server continues to comparing the passwords. bcrypt is utilized to compare the password passed by the user and the hash password stored in the database. If this comparison returns with them matching, the user is then directed to the dashboard component. The sign-up process is also standard, with the user asked to fill in the required fields. That data is then stored within the database and the sign-in process can begin. The dashboard consists of 2 main sections that provide the user the ability to view and interact with the data. The classification section provides the user with a dedicated section of the most recent classification. The user can see the classification results for each event, along with the date and time the classification occurred. The location section consists of both providing the data and allowing the user to interact with it. This section consists of information cards that provide the latitude and longitude for the origin location of that event. A Google map is also implemented, initially only showing the current locations of the sensors. The user can then choose to see a visual of the different event locations with the use of an Add Marker button. Both of the sections consistently update for a specific time interval. The use case shows a simple view of the user's interaction with their web application. The user will first go to the web application's web address and will be presented with the options of either logging in if they are a returning user or signing up if they are new. If the user is new, they will complete the sign-up process and then continue as if they are a returning user. The user will then be brought to a dashboard where they have the ability to access the features discussed previously. The user can then continue to view the presented data or log out of the application.
Our project uses multilateration to compute the origin location of the sound. Multilateration is not quite the same as triangulation because triangulation uses direction and multilateration uses time difference of arrival. The time difference of arrival is the difference in time that a signal arrives at each sensor location. A popular example of multilateration is GPS. GPS uses time signals received from many satellites to compute its location on Earth. Because exact locations cannot be determined for origins outside of the shape, the area encompassed by the sensors, our operating area is limited, and only works for origins within the sensor area. Our measurements are relative because we don't know the time that the sound started at. So we have to use the positions of the sensors and relative time of arrival at each location to determine the absolute time of arrival for each sensor. From there, we use a popular library available in multiple languages such as Rust, C#, and MATLAB to compute the actual location of the sound. To stabilize the locations received from the GPS, we use a Kalman filter. If a measurement has a high possible error, then it only affects the current location slightly. If a measurement has a low possible error, then during the update process, it favors that location much more. We directly use the horizontal dilution of precision within the measurement covariance matrix during the update step. The horizontal dilution of precision is directly provided by the GPS module with each location, and we use a popular C++ library called Eigen, adapted for the Teensy. Each sensor has two microcontrollers using a Teensy 3.2 and an ESP32. Both are pretty well documented, and both are programmed in C++. The GPS data is received on the Teensy via UART from the GPS module, and data is transferred from the Teensy to the ESP32 via SPI. This includes current locations, detection locations, and audio data. From there, data is transferred from the ESP32 to the server using TCP and COBS. COBS is a basic encoding algorithm used to remove zeros from data, which we use on the server to detect how many bytes a packet is. The central server is programmed in Rust, and it receives the current location of each sensor, audio data from each sensor used for classification, and the time and location each sound event was recorded at. It computes the absolute time difference of arrival for each sensor using the relative time difference of arrival and the known location of each sensor. From there, it feeds directly into the UCNL nav library, which internally uses the null-remed iterative method to compute the actual location of the sound. It sends central locations to the web server for display on the map. The audio files used for classification, and it computes the origin location and then sends each origin location to the web server for display on the map as well. Now on to the administrative content. Chris mainly worked on the power and circuit design, and Brandon mainly worked on the circuit design. I worked on the microcontroller programming as well as the multilateration backend. Drew mainly worked on the classification backend and the web interface. Here you can see our project budget, which is somewhat loose because we did have to buy additional parts near the end. Financing was done ourselves, and we basically split it up with one microcontroller per person.
Other than some minor tweaks that could benefit the system in minor ways, all other parts have been implemented completely and successfully. Some difficulties that we have come upon include, for the machine learning aspect of our project, acquiring the amount of data needed and the time-consuming nature of training a model. We have also had some difficulties of creating a robust system of audio fingerprinting due to having to use short audio samples to determine the audio data's time of arrival. This resulted in limiting the signals to be located to a single frequency. There have been some difficulty in being able to accurately test the full capability of our microphones in respect to the distance that will be able to pick up audio. With our MCU, we have discovered some libraries that could be useful but lack any implementation in C++.